Okay, let's unpack this. Today, we are diving deep into a vulnerability that, frankly, sent seismic waves through the modern web development community. It really proved once again that, complexity is the enemy of security. We are talking about a critical flaw that targeted the JavaScript ecosystem, one that instantly earned the terrifying nickname React2Shell.
And it really earned that name.
Absolutely. This is CVE-2025-55182. It wasn't just a bug, it was a crisis. It leveraged a fundamental high-performance optimization in React architecture, specifically React server components, and turned its data pipeline into a globally accessible remote code execution engine.
It's the kind of thing that keeps security people up at night.
For anyone who thought the days of pre-authentication RCE were fading, React2Shell served a brutal reminder that deserialization flaws remain the ultimate prize for attackers.
They absolutely do.
Our mission today is to give you the full picture. We want you to really grasp this event, whether you're a developer, a security analyst, or just trying to navigate this new era of web frameworks. That means we have to dissect the core technologies. What exactly are React Server Components, or RSC, and the flight protocol? We need to go deep into the exploit chain, breaking down how a flaw in data serialization led to prototype pollution and ultimately RCE. And crucially, we need to map out the sheer terrifying speed of the real-world exploitation that followed.
And we really have to emphasize that comparison to Log4Shell because the metrics, they support it entirely. This is maximum severity territory.
A 10.0.
The flawless, terrifying 10.0 on the CVSS scale. That translates directly into unauthenticated remote code execution on the server side. I mean, an attacker doesn't need a valid user. They don't need a password. They just need to hit a publicly exposed endpoint.
And the timeline.
The timeline is what's so frightening. Exploitation began within hours of the initial patch release and public disclosure on December 3, 2025. When a bug is this reliable and this critical, the window for defense is, it's measured in minutes.
And the blast radius is just enormous, affecting the latest React 19 server-side packages, and perhaps most concerningly, due to its sheer ubiquity, the entire ecosystem built around the Next.js app router.
Exactly.
This wasn't some theoretical vulnerability discussed in, academic papers. CISA added React2Shell to the known exploited vulnerabilities, the KEV catalog, almost immediately, confirming sustained and widespread active attack globally. This is the definition of a catastrophic high-priority vulnerability.
It forces instant reaction, immediate patching, and aggressive monitoring. If you run modern JavaScript infrastructure, this one vulnerability dictates the prioritization of your entire security program.
So, to understand how this disaster happened, we have to start at the architecture itself. We're diving into part one, the React ecosystem and the inherent security trade-offs of the flight protocol. For our listeners, let's start with the basics. Modern web development is, well, it's complicated, but React Server Components, or RSC, were created to solve some very real performance problems. What are they, and how did they fundamentally change the job of the React server?
Well, RSC is a massive paradigm shift. Think back to traditional React or Angular. Almost all the component logic ran on the client in your browser.
Right.
That meant developers had to write a lot of code, and all that code plus the data had to be bundled and shipped over the wire. This resulted in these very large JavaScript files that really slowed down page load times.
Yeah, the dreaded bundle size.
Exactly. React Server Components flipped that model. Now, many of those components, especially those that deal with static data or database queries or accessing environment variables, they run entirely on the server side.
And the benefits.
The benefits are clear. Faster performance, smaller client bundles, and the ability to safely access privileged backend resources without exposing keys or secrets to the browser.
So the server isn't shipping executable JavaScript code anymore. It's shipping, a description of the UI. It's essentially saying, here's the structure I built, now you render it.
Precisely. And the transport mechanism for this, the protocol that delivers this description across the network, is called the flight protocol.
Flight.
Yeah, it's a custom, highly optimized serialization format. It allows the server to stream the component data in UI state to the client incrementally, which makes the user experience feel instantaneous. It's designed for speed and efficiency.
That seems like a great optimization, but, where did the security model break down?
The problem wasn't the initial server-to-client flow. The security boundary was shattered during the reply flow, specifically during what React calls server actions.
Server actions.
Right. Server actions allow the client to send data back to the server and trigger remote function calls like submitting a form or clicking a button that runs a privileged action on the server.
Okay, I see where this is going.
To process that client request, the server accepts a serialized flight payload containing the data and the ID of the action to be triggered.
Oh,
React2Shell lives entirely in the deserialization process of that client-to-server reply payload.
so the server takes this data, turns it back into live JavaScript objects, and then runs the logic.
And that's the weak point.
Wait, let me
Go-
pause there because this feels like the critical security trade-off. By allowing the client to send back a serialized payload that the server then automatically reconstructs into functional JavaScript objects,
Yeah.
the server is implicitly trusting that the payload is well-formed and non-malicious.
Yes.
Was this assumption of client trustworthiness that the payload should only originate from a legitimate React client? Was that a fundamental security failure in the design of Flight?
That's a really insightful question, and yes, it highlights a tension inherent in a lot of modern frameworks. When you build a proprietary protocol like Flight for internal communication, developers often prioritize speed and convenience over deep, runtime input validation.
They just assume good faith.
They assume that because Flight is a custom protocol, and because the client-side code would only generate valid references, the server-side deserializer didn't need to perform exhaustive security checks. Things like checking for property ownership or primitive manipulation.
But attackers don't use the legitimate client.
Of course not. They just craft a malicious payload that follows the protocol structure. And that lack of scrutiny during deserialization is exactly what led to the flaw.
So let's quantify the blast radius. Which core packages were carrying this insecure deserialization logic?
The flaw resides deep inside the server-side packages responsible for decoding and processing these RSC payloads. The vulnerability was confirmed in the three primary server packages that handle different bundlers: React Serverdom Webpack, React Serverdom Parcel, and React Serverdom TurboPack.
So the engines that turn the Flight payload back into live objects.
Exactly. And the vulnerable versions were confirmed across the React 19 ecosystem, specifically starting with 19.0.0 and continuing through 19.1.0, 19.1.1, and 19.2.0. If you were running these specific server-side versions, the vulnerable code was loaded by default.
Wow.
It didn't even matter if you had explicitly enabled server actions in every component.
And this leads us to the biggest target, Next.js. I understand the Next.js app router made this an absolute global incident.
Next.js is the most popular framework leveraging RSC, and it became the primary target. It bundles a hardened copy of the RSC implementation, and critically, the vulnerable flow is exposed simply by including a specific header, the next action header, an HTTP request to almost any endpoint using the app router.
Just header.
Just a header. The vulnerable versions include Next.js 15.x before 15.5.7 and Next.js 16.x before 16.0.7, plus some earlier canary releases from 14.3.0 onward. Its popularity and ease of access made it the low-hanging fruit for mass exploitation.
But to be clear, this is a React and RSC problem, not exclusively a Next.js problem.
Absolutely correct. Any framework that embeds or wraps those vulnerable React Serverdom packages is exposed. Public advisories also mention developers using frameworks like Waku, the RSC Preview and React Router, and specific RSC plugins for bundlers like Parcel and Vite.
And other libraries.
Yeah, and libraries like Redwood SDK and Expo, provided they utilize the server component features.
And just for clarity, if you were still pinned to React 18, or if you were using React 19 but rendering strictly client-side without enabling any server components features, you dodged this particular bullet.
That's the good news. If your application renders React exclusively client-side, or if you were pinned to an older version of React 19 without RSC enabled, which is rare for modern deployments, the vulnerable code path was not initiated, and you were likely safe from React2Shell itself.
Okay, let's talk scale and reliability. We've established the 10.0 CVSS score. Now, what do the exposure metrics tell us about the actual risk this posed to organizations?
The risk profile is it's extraordinary. Estimates from security firms like Wiz showed the vastness of the problem. They estimated that 39% of cloud environments globally included vulnerable React or Next.js combinations somewhere in their infrastructure.
39%, that's huge.
And even more concerning, they found that 44% of all cloud environments had publicly exposed Next.js applications. That means nearly half of these deployed vulnerabilities were directly internet-facing. This isn't buried in some internal network. This is sitting right on the perimeter.
That's a massive target. And what makes this vulnerability so dangerous isn't just the scope, but the reliability of the exploit itself.
Precisely. This is what puts in the same category as Log4Shell. This flaw is based on a deterministic logic bug, meaning the sequence of steps to RCE is predictable. It's not messy, unreliable memory corruption that requires specific server operating systems or heap layouts.
So it just works.
Exploitation is described as near 100% reliable, using a single, carefully crafted HTTP POST request. You need no authentication, no user interaction, and it exploits the default framework settings.
That cocktail of factors pre-auth access, remote execution via a standard HTTP request, and a highly predictable logic flaw means automated scanners can sweep the internet and guarantee a successful RCE once an exposed endpoint is identified. It makes the attacker's job incredibly efficient.
It lowers the barrier to entry significantly.
Mm.
I mean, a script kiddie running an off-the-shelf scanner can achieve the same level of access as a sophisticated nation-state actor using this specific vulnerability. And that's what we saw immediately unfold in the wild.
Given that massive exposure and the near-perfect reliability, the next logical question is, how, specifically, did they manage to turn that server architecture and its performance-optimized data stream into a launchpad for remote code execution? So let's put on our attacker hats now. We need to peel back the abstraction layer of Next.js and React and look deep into the JavaScript runtime to understand the exploit chain. This is the heart of the deep dive. We're talking about unsafe deserialization and its most infamous child, prototype pollution.
The entire chain starts with one small yet catastrophic oversight in the core deserialization logic of the flight protocol. The root cause is a logic flaw in a helper function within the React server DOM packages, a function responsible for resolving external references or exports, something probably called require module.
Okay.
The flaw centered on how the code accessed properties when resolving references within the payload. It used bracket notation, export's name, to look up the property specified by the attacker control name field.
And the problem?
Crucially, the code did not check if the property being accessed was the object's own property using the hasOwnProperty method.
That seems like an absolutely foundational security check to miss, especially in a deserialization context. Why is missing that hasOwnProperty check so devastating in JavaScript?
It's devastating because of how JavaScript inherits properties. When you use bracket notation objectee, if that key isn't found directly on the object, the JavaScript engine doesn't stop looking. It walks up the entire prototype chain, the object's parent objects, until it finds a match.
So you can climb the ladder.
You can climb the ladder. And since the name field in that bracket notation was controlled by the attacker's input via the flight payload, they could send a reference name like proto or constructor. This lack of validation, combined with the unsafe deserialization, enabled a full server-side prototype pollution attack.
Let's make sure we ground that concept for everyone. If I pollute the prototype, what does that practically mean for every other object running in that Node.js process?
Think of the JavaScript prototype chain as like the DNA of every object in the process. When an attacker modifies a property on object.prototype, which is the grandparent of almost every object, they have essentially modified the blueprint for all objects that exist or will ever be created in that runtime.
Wow.
They're not just changing one variable, they are planting a hook deep into the foundational engine. This allows them to pivot from controlling data keys to controlling execution logic by poisoning key functions used later in the process.
It's incredibly elegant and horrifying in its simplicity. Now, let's walk through the 4 core steps an attacker takes to pivot that pollution into a remote code execution gadget.
Okay, step 1. Obtain the function constructor, the gadget. The ultimate goal in Node.js RCE is often to gain access to the global function constructor, because new function arbitrary code acts exactly like evil and executes whatever string you feed it.
Holy grail.
Exactly.
Yeah.
To get this, the attacker crafts a specific reference payload that leverages the prototype traversal we just discussed. They often use a path like $3.constructor.constructor, where $3 is just a simple placeholder for an array object. The deserializer starts at $3, which is an empty array object.
So the pass is recursive, essentially. It's climbing on itself.
Precisely. The first .constructor resolves to the array constructor function object. Then the deserializer is tricked into looking up .constructor again on that array constructor. In JavaScript, the constructor of most built-in functions, including array, points back to the global function constructor. So in 4 short tokens, $3 constructor.constructor, the attacker has manipulated the server into retrieving and holding the ultimate RCE primitive, the ability to execute arbitrary code strings. This gadget is now ready to be deployed.
That is truly a textbook illustration of abusing foundational language mechanics. What happens in step 2? They have the function constructor, but how do they get the server to call it with their malicious input?
That's step 2. Inject malicious context. The confused deputy. This is where the prototype pollution comes into play.
Yeah.
The attacker uses the pollution primitive to set up a fake, poisoned internal structure. They specifically target the internal response object, the context used by the deserializer, and poison two crucial properties on it.
Okay, what are they?
First, they change formData.get, which is a function the server normally expects to retrieve form data values.
Right.
They redirect this property to point to the function constructor gadget from step 1. Second, the attacker's malicious JavaScript code say, the command to launch a reverse shell, or process.mainModule.requireChildProcess.xxinc, is smuggled into another field on that fake context object, usually prefix.
So the server starts its deserialization process thinking it's operating on a legitimate context object, but that object is already rigged. The server becomes a confused deputy, carrying out the attacker's wishes by unknowingly using the poisoned context for subsequent operations.
Precisely. The server believes it's calling a standard data retrieval function, .get, but it's actually calling the RCE gadget function constructor. The next trick is forcing the server to actually call this poisoned function.
How do they trigger that complex call sequence?
That's step 3, trigger execution via promises, definable abuse. React Flight, like many modern async frameworks, uses special notation, like $1, to handle asynchronous values or promises within its serialized stream. In JavaScript, any object that has a callable then method is treated as attainable. The exploit is structured to make the deserialized object attainable, which forces the server to process a custom, then call on the poisoned object.
I see. So it's tricking the async logic.
Exactly. By setting up a specific internal state transition, often using a self-referential loop with promise reference like $, the attacker forces React's internal logic, specifically chunk.prototype.then, to execute. This execution path eventually leads to the invocation of an internal function like initializeModelChunk, which initiates a crucial second deserialization pass.
A second pass.
A second pass. This is vital because it reprocesses the payload, but this time it uses the poisoned context we set up in step 2.
Fascinating. So the first pass is just setting the stage and polluting the context, and the second pass is the coup de grace where the execution actually happens.
Exactly. And that leads to step 4, final payload invocation, the RCE. During this second pass, the payload contains a specific marker, a blob reference, often denoted by $, like B23037 others. The vulnerable blob handler logic, which is intended to retrieve the data associated with that blob reference, executes a line of code intended for standard data retrieval. Response.formData.get, response.prefix plus aid.
And we know what those values are now.
Right. Now, let's substitute the poison values. Remember, the attacker set response.formData.get to the function constructor, and response.prefix contains their malicious code string. So that benign data retrieval line translates directly to function malicious code string plus id.
And there it is.
The function constructor is invoked with the full malicious code string, creating and immediately executing the arbitrary payload inside the highly privileged Node.js server process. Game over.
That is an incredible, almost a Rube Goldberg-esque chain. It weaponizes the standard data flow mechanisms of the framework against its own runtime. But we've also seen highly sophisticated variations on the execution primitive itself, moving beyond standard shell commands.
We did. Well, the function constructor is the most common gadget. Skilled attackers immediately branched out. They realized the RSC loader imports the core Node.js VM module.
Oh, that's not bad.
No. By using the same prototype primitive, they could target VM.run in this context, which executes the attacker string payload directly in the current server context, offering a slight increase in stability and stealth compared to the global function object.
But the real game changer was something else.
The real game changer was the emergence of node-native silent exfiltration. This is RCE with like an invisibility cloaking device. Instead of relying on noisy calls to external binaries like binch, bash, or curl.
Things that an EDR would spot.
Exactly. These sophisticated payloads execute entirely in memory. They dynamically load core Node.js modules -node.http, node.fs, node.net directly via process.mainModule.require.
Wait, so they didn't even drop a file or spawn a child process that an EDR system might flag? They essentially turned the running Next.js process into a fully undetectable, self-aware spy agent using the system's own libraries. That is terrifying.
It changes the game for blue teams relying on process monitoring. These in-memory scripts were meticulously designed to harvest maximum value credentials. The execution goals were highly specific. Harvest, etc. shadow if the process was running as root.
Of course.
Enumerate and steal all SSH private keys, looking specifically for Idreza, ITSA, and IDID 25512, and collect the last 1,000 lines of bash history to understand server owner habits.
And how did they get the data out?
Silently, using node zone network capabilities, they constructed the HTTP POST request entirely in memory, using node.http, packaging the harvested credentials into the body and exfiltrating them to attacker-controlled infrastructure, often on non-standard ports on generic IPs, something like 144.91.87.221.9999.
And that just blends in.
It blends in perfectly. Since the Node.js process is an application that is supposed to make network requests, this outbound activity often looks like legitimate back-end traffic.
That level of sophistication, a multi-stage exploit that abuses language primitives, poisons context, and then executes its payload invisibly using native libraries, shows exactly why this 10.0 vulnerability warranted the immediate panic we saw. The technical mechanics are breathtaking, but the real story is the velocity of the attack. React2Shell didn't stay theoretical for long. Let's look at the timeline and the sheer immediate global response.
The timeline is a masterclass in zero-day exploitation velocity. The bug was privately reported and confirmed on November 29, 2025. Patches and public advisories were published on December 3rd, but here's the critical point.
What's that?
Mass scanning and opportunistic exploitation began within hours of that public disclosure, December 3rd.
Hours.
Hours. Defenders had no time. They were scrambling to read the advisory while automated botnets were already integrating the exploit chain. By December 5th, CISA added the CVE to its Secure e-catalog, confirming that the threat was not only being actively exploited, but was deemed a major risk to federal and critical infrastructure.
The industry response was almost instantaneous and demonstrated the sheer scale of the emergency. We have to talk about the Cloudflare incident.
Oh, the Cloudflare incident is a tangible example of the operational severity. The threat was so severe that Cloudflare executed an emergency, highly aggressive web application firewall, or WIV rollout, to block React2Shell payloads globally.
A good thing, right?
Well, this rollout, intended to be a shield, was so broad and complex that it resulted in a 25-minute global outage, impacting approximately 28% of their entire global HTTP traffic.
Wow. A WAF rule change caused a quarter of the internet to briefly stutter. Why was the defense so aggressive and why did it fail?
It was aggressive because the only alternative was widespread RCE across thousands of cloud tenants. The defensive rule had to look for every single possible permutation of the attack tokens we just discussed. The prototype references, the function constructor strings, the VM.run in this context calls.
So it was just too complex.
When you deploy rules that complex and that widely unintended interactions and false positives become almost inevitable, leading to the outage. It underscores that when dealing with application layer RCE on this scale, even defensive efforts carry catastrophic operational risk.
And the numbers of vulnerable systems.
In the immediate aftermath, Shadow Server saw 77,664 vulnerable IP addresses globally by December 5th. While quick patching brought that number down rapidly, Palo Alto Unit 42 confirmed that over 30 organizations were compromised by the initial wave. That's 30 confirmed successful RCE intrusions within the first 48 hours.
So who was leading the charge? We saw both low-end commodity attackers and high-end espionage groups jump in immediately.
The vulnerability was a true equalizer. The initial activity was heavily linked to China-Nexus threat actors, which were observed by various intelligence groups targeting high-value systems.
Any specific groups?
Specific name groups included Lamia, a group often focused on financial services and government supply chains, and Jackpot Panda, known for intelligence collection. We also saw sophisticated initial access brokers like UNC5174 leveraging the flaw.
And other established teams?
Yeah, alongside established espionage teams like UNC6600, which was observed deploying the Minicat Tunneler, a covert custom tool designed for persistent communications that is extremely hard to detect. Iran-linked actors were also very active.
All over it.
Absolutely. The reliability factor made it perfect for mass deployment. The flaw was rapidly incorporated into major botnet campaigns, including RondoDocs and the infamous Mirai.
What were they doing?
They immediately deployed DDoS malware and Linux backdoors on compromised servers to expand their network processing power. We also tracked actors UNC6588 and UNC6603 dropping generic shell backdoors for later use.
Let's detail the post-exploitation phase. Once they had RCE access inside that Node.js process, what were the priorities?
The priority was immediate credential and token harvesting. Attackers systematically scraped every environment variable for secrets, AWS credentials, Docker keys, NPM tokens, Git keys. They weren't looking for user data initially. They were looking for keys to pivot.
And they knew where to look.
A clear sign of cloud-aware threat actors was their systematic accessing of the Cloud Instance Metadata Service at 169.254.169.254. This specific internal IP address gives a cloud instance its temporary IAM tokens.
And that's the key to the kingdom.
Stealing those tokens allows the attacker to pivot out of these compromised web server container and into the organization's wider cloud infrastructure, like S3 buckets or databases. They actively hunted for specific configuration files like oscredentials, .cube, and config cloud to maximize their lateral movement options.
And for monetization, the usual suspect, crypto mining.
Yes, the immediate deployment of crypto mining was widespread. This involved UPX-packed XMRig variants, often compiled for Linux or specific ARM architectures, running against pools like C3 Pool.
And they focus on persistence.
Heavily. They would often use no-hub vart promcron to ensure the miner ran indefinitely, even if the terminal session was killed. Furthermore, sophisticated scripts were deployed that actively scanned the host for and killed competing miners from other attackers, ensuring maximum resource dominance.
We also saw the deployment of very professional, long-term backdoors, signaling intent far beyond simple crypto mining.
That's right. For long-term persistent access, we saw professional-grade tools. This included the deployment of Sliver Implant's advanced, highly flexible 64-bit ELF binaries that use dedicated TLS command and control channels, and Cobalt strike beacons, which are the gold standard for penetration testing and, unfortunately, for advanced adversaries.
And there was one more, right?
Palo Alto also specifically observed the deployment of the Case-Walk Door backdoor, described as a professionally engineered remote access tool designed to build a hidden mesh network among multiple compromised servers.
That points directly to highly organized intrusion goals, establishing a covert long-term foothold. But what was the most sophisticated high-stealth technique observed for persistence?
That goes back to the fileless backdoor, the so-called magic path web shell. Instead of dropping an executable file onto the disk, which traditional endpoint security monitors would flag, sophisticated actors leveraged the RCE primitive to dynamically import core Node.js modules, like node.http.
Okay.
They then performed what is known as monkey patching. They dynamically modified the core Node.js runtime's HTTP server.prototype.emit method. This method is the low-level engine that handles every incoming HTTP request before it even gets passed to Next.js or the application router.
So they're inserting a hook at the absolute base layer of the Node.js server.
Exactly. This in-memory web shell intercepts every request. It only triggers when it detects a specific, predefined, and usually highly obscure magic path, URL- like favicon.login.ico.
And if it sees that path?
If that path is detected, the script executes commands passed via query parameters. If the path is not present, the request is passed up the chain normally. Since the malicious code only exists in memory and is only triggered by that specific path, it is incredibly hard to detect with standard network or log analysis.
And it's ephemeral.
It disappears completely if the server instance is rebooted or recycled.
A completely stealthy, fileless, memory-resident backdoor. It truly demonstrates the power and the ultimate danger of unauthenticated RCE inside modern application runtimes. Now we shift our focus to the crucial question for security teams, developers, and frankly, the business leadership footing the bill. So what does this all mean for us? Let's translate this complex technical exploit into clear, tangible business risk scenarios.
The first and most immediate is the front end to cloud control plane compromise. You have to remember where these modern Next.js apps run in ephemeral containers like Docker or Kubernetes on cloud platforms like AWS, Azure, GCP.
Right.
These containers are transient, but they often possess temporary highly privileged credential, IAM roles, that allow them to talk to adjacent services.
So the RCE on that Next.js front end is the gateway.
It's the gateway. An attacker uses that access to steal those temporary IAM credentials from the cloud metadata service we mentioned earlier. They pivot instantly from exploiting a web bug to initiating a full cloud account breach. This means they can access sensitive data in S3 buckets, shut down databases, or launch new malicious infrastructure. A front-end vulnerability becomes an entire infrastructure disaster.
The blast radius expands significantly in shared environments too.
That's scenario 2. The multi-tenant SaaS blast radius. If a software-as-a-service provider runs vulnerable React Next.js front-ends in a shared multi-tenant environment, a single React2Shell exploit can allow an attacker to achieve tenant-to-tenant pivoting.
meaning they can jump from one customer's data to another.
Exactly. By gaining RCE, the attacker can access shared resources, extract data belonging to multiple customers simultaneously, or poison shared components consumed by other tenants. This immediately elevates the incident into a large-scale supply chain breach, affecting dozens or even hundreds of customers at once.
And the financial and reputational damage.
It's multiplied exponentially.
And finally, the regulatory and operational headaches.
That's the compliance and outage pain. Pre-auth RCE on systems processing PII, especially in sectors like finance, healthcare, or retail, results in immediate massive regulatory exposure under regimes like GDPR, EPI, or PCI DSS. The mandatory reporting requirements are instantaneous, and the fines can be crippling.
And the operational side.
The operational fallout is severe, as the Cloudflare outage showed. Organizations had to justify emergency maintenance windows and rush patches, impacting service availability and customer trust. You need to be able to translate a 10-point-A CVSS score into board-level risk.
Given the gravity, let's talk mitigation. What is the single, non-negotiable step required to defeat this vulnerability?
Patching is mandatory, and it is the only definitive fix. You must update the core vulnerable server-side packages, the React Server libraries, and all dependent frameworks. This means moving to Next.js 16.0.7 or later, or the equivalent patched versions in the 15.x branch, and React 19.2.1 or later.
And it's not just about changing a version number.
We have to stress this because it's a point often missed by automated tooling. Simply updating the dependency version number in your package.json file is insufficient. The application containing the vulnerable code path must be fully rebuilt and redeployed to ensure that the server-side bundles incorporate the patch deserialization logic.
So if you don't rebuild, you're still vulnerable.
If you just update the version number and don't rebuild the deployment artifact, the vulnerability often remains.
And the credential issue, given the fileless harvesting we saw.
Immediate credential rotation is non-negotiable because RCE allows full access to the process memory and environment variables. Organizations must operate under the assumption that all API keys, database secrets, and cloud access tokens exposed in the server runtime were compromised immediately after the December 3rd disclosure.
Do it before anything else.
Rotation must be prioritized and completed before you even assume the patch is successful.
Moving to detection, the fileless nature, the use of memory-resident backdoors, and the fact that these apps often run on ephemeral infrastructure like Kubernetes or serverless make this incredibly difficult to catch. How do security teams find the invisible attacker?
The difficulty is immense. If the attacker executes a clean RCE and immediately harvests credentials before the container recycles, the evidence is just gone.
Right.
Therefore, detection needs to happen at multiple layers, starting with prevention and inventory.
So step one.
Build pipeline and inventory checks are step one. You must use software composition analysis, SCA tools like Sift, Trivy, or commercial equivalents to scan your package.json and lock files for the specific vulnerable versions of React Server Webpack, Parcel, or TurboPack. If they are found, the build must fail.
What about the network boundary? Is there any way for IDS to reliably spot the exploit payload itself?
At the network level, WAF and IDS signatures must be incredibly specific and detailed. You need to look for PUST requests targeting known RSC endpoints, typically paths starting with next or AP, that contain the required action headers, like next action or RSC action aid.
And in the payload.
More importantly, you have to look deep into the payload body for the attacker's toolkit. Add tokens, which signal the uneditable abuse, and the signature strings referencing JavaScript internals like constructor, proto, VM, or run in this context.
But WFs have their limits.
They do. And we must discuss the limitations of WAFs later because, as we saw, these rules are brittle against application protocol flaws.
So we need to focus on runtime detection, trying to catch the execution itself.
Absolutely. On the host level, EDR and audit logs must be configured to monitor for highly suspicious behavior originating from the Node.js parent process. This includes new, unauthorized processes spawned by Node.js, which is a sign of a reverse shell or crypto miner. Unusual file modifications in temporary directories, or critically unauthorized outbound network connections to non-standard ports or known malicious IPs.
And the cloud metadata service.
Yes. We must also prioritize monitoring cloud audit trails for access attempts to the internal metadata service URL, 169.254.169.254, originating from the web app instance. That access is a direct indicator of cloud credential harvesting and warrants immediate investigation.
Now, you mentioned a highly sophisticated safe method for verifying exploitability without actually running malicious code, the safe side channel check. How does that work in practice?
This is a high-fidelity technique used by security researchers and modern scanners. Because the vulnerability is a deterministic logic error, it causes a specific failure when property checks or skip scanners can trigger that failure without executing RCE. They force a payload, for instance, a reference like $1 non-existent.property, which attempts to look up a non-existent property on an object. In a vulnerable server, the flawed logic skips the necessary property ownership checks, attempts to resolve the reference, and fails in a specific way that crashes that part of the deserializer.
So the crash is the signal.
Exactly. This predictable failure causes the Next.js server to return a specific HTTP 500 internal server error, often coupled with a distinct error digest. A patched server, however, correctly performs the ownership checks, handles the non-existent property gracefully, and returns a standard application error or a 200 OK.
So you look for the 500 error.
By looking for that specific 500 crash signal in digest, security teams can safely and reliably confirm vulnerability in production without ever triggering the RCE payload.
That is a remarkable technique, turning an application crash into a reliable indicator of security status.
It allows you to scan production safely, which is invaluable during a crisis like this.
Now, we need to address the WA arms race because the response from the industry leader here was frankly shocking. We have to discuss Vercel's $750,000 WAF bounty program.
Right. Vercel, which manages Next.js, launched an emergency program through HackerOne that was dedicated solely to researchers finding bypasses to their emergency web application firewall rules for React2Shell.
This wasn't for the root cause.
No, that was already known and patched. This was a race against the offensive community to validate their perimeter defense.
And the results of that 24-hour program were immediate and sobering.
They were. Within approximately 24 hours of launching the program, researchers had already reported 15 unique WAF bypasses. These weren't subtle changes. They were clever encoding tricks, payload splits, and new ways of referencing the exploit tokens that Vercel's aggressive WAF rules simply hadn't accounted for.
That is nearly $750,000 spent in a single day just to patch the patch. What does that tell us about the utility of WAFs when facing complex application layer protocol flaws like this?
It tells you two things very clearly. First, it proves that React2Shell was treated as an existential threat, justifying an incredible financial outlay just to gain a few hours of breathing room for their users to patch.
And the second thing?
Second, and more importantly for defenders, if a top-tier platform with elite security engineering staff must spend $750,000 to keep up with 15 unique bypasses in one day, it demonstrates that generic WAF rules are fundamentally brittle against flaws that live deep within a complex, proprietary application protocol like Flight.
So they're not a silver bullet.
WAFs are excellent for preventing simple cross-site scripting or SQL injection, but they struggle severely when the exploit token can be hidden in complex serialization formats, split across multiple parameters, or simply encoded in a way the rule engine wasn't explicitly programmed to block. The lesson is clear. WAFs are a necessary temporary shield, but patching the root vulnerability in the source code remains the only sustainable long-term defense.
It reinforces the idea that complexity at the application layer inherently opens up pathways that perimeter defenses often cannot fully anticipate. React2Shell is already a legendary case study in modern web security. A seemingly small logic flaw, the omission of a simple has-own property check-in, a highly optimized, developer-friendly abstraction like React Server components, mutated rapidly into a critical, unauthenticated RCE at massive production scale.
It's a textbook example.
It highlights the profound danger inherent in insecure deserialization across all languages, especially when handling non-standard, complex protocols like Flight. The speed and sophistication of the attackers demonstrated that there is zero grace period for vulnerabilities of this caliber. If you are running React 19 or Next.js app router deployments, patching, rebuilding your application, and immediate secret rotation should have been your primary non-negotiable priority following the disclosure. The cost of a few hours of delay, as we've seen, can be a complete cloud account breach.
The central feature of React2Shell was its reliance on abusing foundational JavaScript concepts. The prototype chain, bracket notation traversal, and the global function constructor. We rely on modern frameworks to abstract away complexity and provide a secure environment. But React2Shell showed us that if a performance-optimized web architecture designed for developer experience can be completely dismantled by manipulating a basic data retrieval function, it forces us to re-examine the implicit trust we place in the internal design of the languages and frameworks we use every day.
We just treat them as black boxes.
We treat the framework as a secure black box, But the exploit showed the vulnerabilities lie in the language primitives beneath the abstraction layer. The critical question remains: are we doing enough to scrutinize the security implications of these foundational language features, the proto and constructor, that every modern application inherits, or are we just hoping they hold up under fire?